Section 5.5, inequalities in a triangle. The comparison property states if A is equal to B plus C and C is greater than 0, then A is greater than B. This property is used to prove the corollaries that follow this slide. The proof of that is on page 289. Also, if we take a look at a comparison property in relation to the transitive property, it can be stated that if A is greater than B and B is greater than C, then A must be greater than C. Our first corollary is to the exterior angle theorem. The measure of an exterior angle is greater than the measure of each of its remote interior angles. If we recall, the theorem itself for the exterior angle theorem is an exterior angle is equal to the sum of the remote interior angles. So in this diagram, we could state that the measure of angle 1 equals the measure of angle 2 plus 3. Therefore, it does make sense that the exterior angle is greater than either of the two parts that make up that angle. In other words, what we have is the measure of angle 1 is greater than the measure of angle 2, and the measure of angle 1 is greater than the measure of angle 3. Let's take a look at an example of this corollary. In this diagram, we want to list all angles less than angle 1. Here, angle 1 is an exterior angle to the small triangle. Therefore, angle 1 must be greater than angle 4 and angle 3. And that's based on the corollary to the exterior angle theorem. The exterior angle is greater than either remote interior angles. But we're also given that these two lines are parallel. And I know another theorem from a previous chapter. If two parallel lines are cut by a transversal, then corresponding angles are congruent. So I know that angle 4 is congruent to angle 5. And by the comparison property, if angle 1 is bigger than 4, 4 is congruent to 5, then angle 1 must be greater than angle 5. Also, within this diagram, I know that angle 1 is obtuse. Since 1 and 2 are a linear pair, that means that when I use the angle addition postulate or the definition of a linear pair, 2 must be less than 1. Also, as we have here 5 congruent to 4, again, we have two parallel lines, and if they are cut by a transversal, again, corresponding angles are congruent. And I know from that theorem, angle 6 is congruent to angle 2. I know that angle 1 is greater than angle 2, therefore it must be greater than angle 6. Theorem 510. If two sides of a triangle are not congruent, then the larger angles lie opposite the longer side. Here we're given in the diagrams triangle ZYX. What is known to be true in that triangle is that segment XZ is greater than segment XY. If that's true, then the angle opposite XZ is greater than the angle opposite XY. XZ, the angle opposite XZ, is angle Y. The angle opposite XY is angle Z. Therefore, I know from this given theorem that angle Y is greater than angle Z. I like to refer to this theorem as the angle inequality theorem. We know that the largest angle lies opposite the longest side in the triangle. Let's take a look at an example. Here we're given triangle RGY, and we're given the lengths of each segment, RG being 14, GY 12, and RY 20. They want us to determine the angle measures from largest to smallest. The easiest thing to do is to draw a triangle. I'm not worried about the proportion. I'm going to use the side measures and the angle inequality theorem to determine the largest and smallest angle. Here are G, Y. RG is 14, GY is 12, and RY is 20. And I want to order from largest to smallest angle. I know the largest angle is opposite the longest side. The longest side is RY, therefore the biggest angle must be angle G. And that angle is bigger than the other two angles, and between those two angles, RG is a longer segment than GY. Therefore, angle Y is next. And the smallest angle must be angle R. Now they're ordered. Angle G is greater than angle Y, which is greater than angle R. I named theorem 510 the angle inequality theorem. Therefore, I'm going to name theorem 511 the side inequality theorem. Here it's stated, if two angles of a triangle are not congruent, then the longer side lies opposite the larger angle. In other words, the longest side is opposite the biggest angle. In this diagram, triangle ABC is given, and in that triangle, I know that the measure of angle A is greater than the measure of angle B. Therefore, by this theorem, the side opposite angle A, which is BC, must be greater than the segment opposite angle B, which is AC. Therefore, I have segment BC is greater than segment AC. Let's look at an example based on the side inequality theorem. Here we're given triangle LMN with the measure of angle L equal to 36 degrees, the measure of angle M equal to 98 degrees. And we want to order the lengths of the sides from smallest to largest. Let's draw a triangle. I'm not worried about the proportion. The measure of the angles will determine the lengths of the sides. Here I have vertices L, M, and N. The measure of angle L is 36 degrees. The measure of angle M is 98 degrees. And I know in my diagram that this is an acute measure, or at least looks like an acute angle, but this is 98 degrees, and we're going to use that to solve my problem. Now I need to use the triangle sum theorem to determine the measure of angle N. 98 plus 36 is 134. 134 from 180 gives me 46 degrees. From the side inequality theorem, I know that the largest side is opposite the biggest angle. Therefore, the smallest side must be opposite the smallest angle. Therefore, my smallest angle in my diagram is angle L. Therefore, the smallest side must be MN. And segment MN is less than the next smallest angle would be angle N. The side opposite angle N is LM. And that leads to our biggest side, which is opposite the biggest angle, which is LN. Therefore, the order from smallest to largest of the segments in this triangle are segment MN is less than segment LM, which is less than segment LN. Theorem 512, the triangle inequality theorem. To form a triangle, we must have this situation occur. The sum of the lengths of any two sides of a triangle must be greater than the length of the third side. If this is not the case, then the three segments cannot form a triangle. In other words, if I just had one segment and these two segments were smaller than this side, if I started drawing them in together and collapsing them toward the vertice, they would not touch. There would be a gap in between here, and you'd end up with parallel segments. In other words, I need to have segment XY plus YZ greater than segment XZ, YZ plus ZX greater than YX, ZX plus XY greater than ZY. The easiest way to determine this is to find the two smallest segments in the triangle, add them together, and if those are not bigger than the third side, then those segments do not form a triangle. Let's look at an example. Can a triangle have sides with the given lengths? Number one, I'm given segments of length being 3 centimeters, 3 centimeters, and 8 centimeters. We need to find the two smallest lengths, add them together, and see if they're bigger than the third side. Here I have 3 plus 3 is 6. 6 is not greater than 8. So these three segments cannot form a triangle. So the answer is no. And I always try to find the smallest sides first, because if I took these two segments, 3 plus 8 is 11, that's greater than the third segment. And then these two would be 3 plus 8 is 11. It's greater than this segment. So if you find the smallest two, that's the quickest way to go at it. On example 2, I have segments that are all equal, 5 inches. 5 plus 5 is 10, is greater than the third segment. If we follow that with the next two segments, I'm going to end up with the same thing. Either two segments, when added together, will always be greater than the third segment in this set. So therefore, yes, these three segments could form a triangle. Number 3, 7, 7, and 14. Remember, the theorem states that any two segments must be greater than the third. Here, when I add the two smallest, 7 plus 7 is 14. 14 is not greater than 14. So that does not follow the theorem. So the answer here is no. These three segments could not form a triangle. Number 4, 5, 12, 13. Again, the easiest way to do this theorem is to add the two smallest segments together. Here, that would be 5 and 12. 5 and 12 add together to equal 17. 17 is greater than 13. So yes, those three segments could form a triangle. On this example, we're given the lengths of two sides of a triangle. They want us to describe the possible lengths for the third side. We have two ways of creating a triangle given a 7-inch segment and an 11-inch segment. I can create a triangle with an unknown smallest segment. In other words, I can let x be the smallest segment and then have 7 inches and 11 inches. Or I could have 7 and 11 be the smallest segments, and I need to determine the largest segment. How do I find the smallest segment if given 7 and 11? To do that, I just take 11 minus 7 and get 4. Therefore, my values of x have to be x greater than 4. The example would be 4 plus 7 is 11. That sum is equal to the third segment and cannot form a triangle. Therefore, x has to be greater than 4. For example, 4.1. 4.1 plus 7 is 11.1. That sum is greater than 11. Therefore, by the triangle inequality theorem, that could form a triangle. To find the largest segment, I would just take these two segments and find their sum. 11 plus 7 is equal to 18. X must be less than 18. If it's equal to 18 or greater, 7 plus 11 is 18. That would equal 18, and therefore, by the triangle inequality theorem, the sum of any two sides must be greater than the third side. And if x is less than 18, that would work. Therefore, x must fall between 18 inches and 4 inches. For example 2, I can determine the smallest segment given 35 meters and 52 meters, and I could determine the largest segment given 35 meters and 52 meters. Letting those segments be represented by x. To find the smallest segment, I have 52 minus 35. When I find that difference, x must be greater than 17. If x is greater than 17, then this value of x plus 35 will be greater than 52, and that fits into my triangle inequality theorem. For x being the largest segment, 35 plus 52, x must be less than that value, and that value is 87. And if x is less than 87, the sum of the smallest two segments will be greater than the third segment, and that would form a triangle based on the triangle inequality theorem. Therefore, x must fall between 87 and 17. On this slide, we're asked if each diagram were drawn to scale, which numbered angle would be the largest? Remember, by the angle inequality theorem, the largest angle is opposite the longest side. Here, I'm given an isosceles triangle. Therefore, I know that angle 1 and 3 are congruent based on the isosceles triangle theorem. If two segments of a triangle are congruent, then the angles opposite them are also congruent. But on this triangle, 13 is my longest segment of the triangle. Therefore, the largest angle of the triangle is opposite that segment. Therefore, the largest angle is angle 2. In this triangle, my lengths of the segments are unknown, but I am given a variable representation for each. Here, this segment is x, then x plus 1, and x minus 1. If I just let x equal some arbitrary number, for example, 5, then this segment would be 5, this would be 6, this would be 4. And by the angle inequality theorem, the largest angle is opposite the longest side. The longest side is represented by the expression x plus 1. Therefore, the biggest angle must be angle 1. In this example, if each diagram were drawn to scale, which segment shown would be the largest? Remember, by the side inequality theorem, the longest side is opposite the largest angle. And in triangle DEF, we're given an angle with a measure of 60 and two unknown measures. But we can determine what the value of k is and find out what the value of these two angles are. I know by the triangle sum theorem, the three angles must add up to 180. Therefore, k plus 2 gives me 2k plus 2 plus 62 will equal 180. And when I subtract, I'm going to get 2k equal to 118 degrees. And when I divide by 2, I'm going to get the value of k. And here, the value of k is going to equal 59. Therefore, angle D is equal to 59 degrees. And angle E is equal to 61 degrees. And by the side inequality theorem, the longest side is opposite the largest angle. Therefore, segment DF is the largest segment in this triangle. On the next example, I'm given the figure WRST. I have WSR being an equilateral triangle. I know that because of the triangle sum theorem. 60 plus 60 is 120. From 180 leaves me 60. Three congruent angles. I have three congruent sides. Therefore, WS is congruent to SR, which is congruent to WR. On this triangle, WTS, I have two angles that are known, 54 and 65. When I add those two together, I'm going to get 119. 119 from 180 leaves me a 61 degree angle. In this triangle, I know the biggest side has to be WT. Therefore, WT is bigger than the next biggest side in this triangle is WS. But I know WS is congruent to RS and RW. And WS is greater than ST. And this is all known by the side inequality theorem. The largest side is opposite the largest angle. Therefore, the largest segment in this four-sided figure is WT. In this example, I still want to find the largest segment. I'm going to start with the bottom triangle. In the bottom triangle, the largest segment is opposite the largest angle. D is my largest angle. Therefore, in this triangle, OC is the largest segment. Therefore, I can eliminate segment OD and DC. Now I'm left with segment OC being the largest at this point. But in this triangle, OC is not the largest segment. The largest segment is opposite the largest angle. The largest angle is at C. So therefore, the largest segment is OB. I can eliminate segment OC and CB. Now I'm left with one triangle. In that triangle, I have the largest segment, which is opposite the largest angle. The largest angle is going to be B. Therefore, the largest segment must be OA. Therefore, the largest segment is OA.